In this lecture, we will discuss regarding the buck boost converter. So this buck boost converter is also a type of DC-DC converter, and the function of DC-DC converter is to transfer the variable output voltage from the fixed input DC voltage. Now this converter can be operated in two modes. First is in step up mode and second is the step down mode. In step up mode, the voltage output voltage across the load will be more than the input voltage, and in step down mode the output voltage across the load will be less than the input voltage. So let me draw the circuit diagram of the buck boost converter. So as shown here, that we have the following components, as we have a supply voltage Vs, then we have a switch. This switch is nothing but it is a semiconductor device which can be either MOSFET, IGBT or transistor. So any type of these semiconductor devices can be used in this place, and once we supply a trigger pulse to these semiconductor devices, then that can be switched on or switched off. So that is has been represented here by a switch. Now there is an inductor L and capacitor C, load, output voltage of the load is V0, charging current IC, load current I0, and there is diode D. Output inductor current is shown by IL. So once this switch is in on position, then the diode D will be reverse bias. So this part of the circuit will not be in the function, and we have actual circuit which is come into the picture has been shown here. It means we have a voltage source Vs, then a switch and an inductor. So if this switch is on position, it means these two terminals will be closed. So supply voltage will be applied across the inductor and current will flow like this. Current will flow like this. It means we can apply the KVL across the circuit, and if you apply a KVL across the circuit, we can see that minus Vs plus V0 equals to minus Vs plus VL equals to 0, or we can say that Vs equals to VL. What is Vs? Vs is the supply voltage and VL is the voltage across the inductor. Similarly, we can apply a KCL across the junction, that is IC equals to I0. IC equals to I0. So it can be seen here that we have a Vs equal to VL and IC equals to I0. So this is the circuit diagram. This is the buck boost converter. All the components which has been shown here for the buck boost converter, that has been reflected here. And once switch is on position, then circuit which comes into the picture has been shown here, and their equations are shown here. Vs equal to VL and IC equal to I0. In next case, we will see when switch is in off position. So when switch is in off position, that has been shown here. When switch is on position, then this part of the circuit will come into the picture. We have an inductor L, we have a diode D, we have a capacitor C, and load is connected here across the capacitor. Then VL is the voltage across the inductor, IC is the charging current, I0 is the load current, and V0 is the voltage applied across the load. This is the IL, that is the inductor current which will be flowing like this. So if you apply the KVL across this circuit, we can simplify it. We can write here that VL plus V0 equals to 0, or VL equals to minus V0, where VL is the voltage across the inductor and V0 is the voltage across the load. Similarly, if you apply the KCL, that is Kirchhoff's current law, across the junction, so what we can write here? That IL equals to I0 minus IC, or IC equals to I0 minus IL, where IC is the charging current, and I naught is the load current, and IL is the inductor current. So this is how we have derived the voltage across the inductor and current across the capacitor during the switch on position and switch off position. Now we will see how to find out the voltage transfer across the load when switch is on or off position. So we can state the voltage second equation. This is called the voltage second equation, in which integration of inductor voltage across the circuit should be equals to 0. It means integration of VL dt should be 0, or we can define that VL on dot T on plus VL off dot T off should be equals to 0. What is VL on? VL on is the inductor voltage when switch is on position, and what is T on? T on is the time duration for which switch remains in on position. What is VL off? VL off is the voltage across the inductor when switch is off, and T off is the duration for which switch remains off. So already we have derived that what is VL on? VL on is equal to Vs and VL off equal to minus V naught. So if we put these values in this equation, so what we can see here, that Vs dt plus minus V naught 1 minus d into t, this should be equals to 0, or we can say V naught equals to d upon 1 minus d dot Vs, where V naught is the voltage across the load, Vs is the supply voltage, and d is the duty ratio of the buck boost converter. So what is duty ratio? It means by varying the duty ratio, this converter can be operated either in buck mode or in boost mode. So how we'll see this can be operated in buck mode or boost mode. Here we see that this is the output voltage equation, V naught equal to d upon 1 minus d dot Vs. So for the case of buck mode operation, if we adjust the value of d between 0 to 0.5, then this converter can be operated in buck mode, or we can say in step down mode. So for the step down mode operation, if we choose the d value of d equal to 0.4 and put this value in this equation, so what we can write? We can write here V naught equal to d times Vs upon 1 minus d, or once we put the value of d, it will be equal to 2 by 3 Vs. This indicates that output voltage is less than the input voltage, because Vs is the supply voltage. So this is output voltage is 2 by 3 times Vs. It means output voltage will be less than the input voltage. Now if this converter is operated in the boost mode, then we have to adjust the value of d between 0.5 to 1. So in this case, if you take a value of d equal to 0.6 and you put this value in this equation, so what we will find? We can see here V naught equals to d times Vs upon 1 minus d, or this is the value of 3 by 2 Vs. What is Vs? Vs is the supply voltage. So what we can see from this equation, that output voltage is greater than the supply voltage Vs. It means in this case, this converter is operating in boost mode. So both the operation can be satisfied by having a value of d equal to 0.4 and value of d equal to 0.6. Now we will draw the waveforms of the buck boost converter. So already we have drawn here the waveform, and this waveform can be drawn in different modes like a T on, T off, T on, T off. In first case, we see that when switch is in on position, then inductor current will rise linearly till the switch remains in on position, and when switch is off position, this inductor current will decay. Further, this rise and decay will be repeated in the next cycle. So what we see that Inductor current fluctuates between two peaks, that is IL max and IL minimum. Similarly, we can draw the diode current. As we know from the circuit that diode current will flow only when switch in up position. So that's why we have seen here that that ID current, that is diode current, has been shown here when switch is in up position, and here also when switch is in up position. So these are the waveforms for the buck boost converter. Now operation control has been demonstrated in this lecture. If you like this video, then please subscribe this channel and share this video to other members so that they can receive the upcoming video.